The title of the lab is the decomposition of hydrogen peroxide, which is same thing as H2O2. The reference was Advanced Chemistry with Vernier, and the purpose of the lab was too many, right? So we're gonna summarize like this to calculate the activation energy. Now it's simple, right?
First is the procedure. You will need a vernier computer interface, a vernier gas pressure sensor, a thermometer or temperature probe, one hole rubber stopper, a plastic burette pipette, and 1 liter beaker. You'll then need 3% hydrogen peroxide and 0.5 concentration of potassium iodide.
Don't forget your goggles and apron too.
Measure out 4 milliliters of 3% hydrogen peroxide solution into the test tube. Seal the test tube with the solid rubber stopper and place the test tube in the water bath. Measure out 2 milliliters of 0.5 concentration potassium iodide solution in a graduated cylinder. Draw 1 milliliter of the potassium iodide solution into a burette pipette, then place the end into the water bath. Connect the vernier computer interface to the gas pressure sensor, and then connect the gas pressure sensor to the 1-hole rubber stopper. Be ready to begin collecting data. The following should be done quickly. Remove the test tube from the water bath and remove the solid stopper. Remove the burette pipette from the water bath and quickly transfer 1 milliliter of potassium iodide solution into the test tube. Tap or lightly shake the test tube to mix the reactants. Seal the test tube with the 1-hole stopper connected to the gas pressure sensor. Place the test tube back in the water bath and begin the data collection for 3 minutes. Once done, examine the graph on the vernier computer interface and record the slope as the initial rate of the reaction.
So for the data table, we are gonna use the sample data for temperature and initial rate, and for data analysis part as well. So the analysis. Question number 1. Calculate the initial rate in moles over liter times second for part 1. Whenever you're given a unit in the question, keep it in mind because we need them to find what kind of equation we're gonna use. So let's look at the data table. So we're given temperature and pressure in kPa, and we know the gas constant, and what we're looking for is moles over volume. We are given temperature and pressure in kPa from the initial rate, and we know the gas constant. What we're looking for is moles over volume. So pressure, volume, moles, gas constant, temperature, PV and RT, equivalent art. Because we are looking for moles over liters, volume, change the equation around a bit like this. Pressure is 0.22 kPa over second. We're going to keep the seconds because the final unit has the second in it. Gas constant 8.314 kPa liter over mole K, but it has to be in terms of kPa instead of ATM, what we usually use, since the pressure is in kPa. Temperature is 292 Kelvin. What we measured is in Celsius though, but the gas constant is in terms of Kelvin, so we need to convert to 73 times plus 19 Celsius is equal to 292 Kelvin. Now you just plug in numbers back to the Pivot equation. Moles over liter is equal to P over RT. kPa cancels out and Kelvin cancels out, and you're left with 9.06 times 10 to the negative 5 moles over liter times second. Always make sure if the unit is correct. So question number 2, determine the order of the H2O2 and minus for the reaction. Justify your answer with math or words. Write the rate law. So we're going to use trial 1 and 2 for H2O2 and trial 1 and 3 to I minus. So let's look at the data table. So I minus concentration is constant, so we're going to ignore that. H2O2 concentration is doubled from part 2 to part 1. Initial rate is doubled from part 2 to part 1. So double H2O2 is in first order. Let's look at part 1 and 3. H2O2 is constant, so we're going to ignore that. I minus is doubled from part 3 to part 1, and initial rate is doubled from part 3 to part 1. So doubled and doubled again, so I minus is in first order as well. So because H2O2 is in first order, I minus is first order, so overall ratio is K times H2O2 to the first power, I minus to the first power. So overall order is in second order.
For the last question, you'll need to use the data to determine the activation energy used in the Arrhenius equation. The Arrhenius equation is ln rate constant 1 over rate constant 2 equals activation energy over gas constant multiplied by 1 over temperature 2 minus 1 over temperature 1. Plugging in the numbers, this will be ln 6.47 times 10 to the negative 4th over 1.31 times 10 to the negative 3rd equals activation energy over 8.314 multiplied by 1 over 302.2 minus 1 over 292. So once you solve for the activation energy, you'll be left with 5.07 joules over moles.